In this video, we are going to go over section 11.1, which is improper integrals. So the goal of this section is to solve problems involving improper integral, meaning instead of a number like integrating from 3 to 5, we have like 3 to infinity, or negative infinity to some number 0, or negative infinity to infinity. So the idea is we have done definite integral, which is integrating something from a to b of f of x dx on closed interval from a to b. This is something that we have done it before, definite integral. Now this idea will extend to going to infinity. Rather than stopping at certain number, we'll start from a to infinity. F of x dx, indefinite length. Okay, so we have three theorems, three definitions. The first case is going from a to infinity. So you cannot really pick a number to plug it in infinity, like what we did with here. We plug it in a and b. So since we cannot really pick a number for infinity, we are gonna approach taking the limit, because limit means we are taking the value to the very end. So we are going to rewrite this infinity as some given value b, where b approaches to infinity. So we'll apply those limits when we are dealing with improper. Same thing here. This time the issue is negative infinity. So we give this number a, and then we'll apply the limit as a approaches to infinity. And the part C is when you have a negative infinity to positive infinity, we'll just pick a point C randomly between an interval negative to infinity and then separate into two different improper integral and then apply the limit. Okay, so let's start with a couple example here. I have a 5 example together, and then you guys can use this one to help solve the homework problems. Number 1, evaluate the integral 1 to infinity of x cubed dx if it converges. Sometimes you might have a conversion, sometimes you might have divergent. It's possible to have divergent because we are taking infinity. So I'm looking at this. This to me looks like the very first example where we have lower limit defined and then upper limit not defined but infinity. So I'm going to rewrite this by writing as limit as, so this will be case 1, right? B approaches to infinity, 1 to b, x cubed dx. Now, let's take the integral. This is an easy integral, x cubed dx. If you take the integral, you raise power divided by new power, so that will be x to the 4th divided by 4, evaluating from 1 to b. So let's keep going. So I'm gonna have b to the 4th over b minus 1 to the 4th over 4. Let's simplify what's inside. We have a common denominator, so we can combine into 1, b to the 4th minus 1 over 4. Okay. Now, if I take the limit of this value here, I have infinity to the 4th power, which is very big number, take away 1, that's still infinity. Infinity divided by 4 is still big number. So the limit of b to the 4th minus 1 over 4 is infinity. So what does that mean? This is a divergent integral. Diverges. Okay. So what we have to do from definite to improper is just take one step of rewriting those indefinite value into a limit, and then go from there. So let's try a second problem. Similar thing. we have an issue of this having the infinity on the upper limit. So I'm going to rewrite as limit as b goes to infinity 16 to b x to the 5 over 4 dx. Now this right over here, the root, you can rewriting using exponent. I prefer using an exponent, rewriting it, because it's easier to integrate. So let's integrate the function limit as b goes to infinity. Now this is just power rule. Add 1 divided by new power. 5 over 4, adding 1, which is 4 over 4, that's 9 over 4. So I'm going to have x to the 9 over 4 divided by new power, so you can rewrite that as 4 over 9. Going from 16 all the way up to some number b, really large number. Applying, evaluating, I have 49 b to the 9 over 4, right? And then subtract 16 over 9, 16 raise it to 9 over 4. Let's keep going. Limit as b approaches to infinity, 4 over 9. Now this number here, 16 raise it over 9 over 4. You can think of it as taking the fourth root of 16, which is 2 to the 9. So 49, b raise it to 9 over 4 minus 2 to the 9, which is some number. Now let's apply the infinity. If I plug it in infinity over here, over where the b is, I'm going to have some big number, take away just a number, and multiply by 4 over 9. So really, this turns out to be, again, just infinity. So the integral diverges. Okay. So example 1, example 2, we both saw that it diverges. Let's take a look at example 3. Now you can see that my infinity is on the lower limit. So this is case 2, where you have a negative infinity to certain number. Negative infinity to certain number. So I'm going to rewrite it as limit as a approaches to negative infinity. There should be a negative right there. It's a typo. There should be a approaches to negative infinity of a to b f of x dx. All right, so rewriting limit as a approaches to negative infinity by one of the rule that we discussed in the past semester. I can move the 7 out because it's a constant. You don't have to, but I just like having that out so it looks simple. A to 0 e to the x dx. Now let's apply integral, which is e to the x is just e to the x from a to 0. Keep going. Limit as a approaches to negative infinity. We have 7 e to the 0 minus e to the a. Okay. Now, anything to the 0 power is 1. E to the a is just e to the a. 1 minus e to the a. Now let's plug it in negative infinity here. So you have 7, 1 minus e to the negative infinity, which can be rewritten as 1 minus 1 over e to the infinity. Negative power rewriting into positive power. 1 over really big number is just this part here is a 0, 1 over really big, large number. So I'm having 7 parentheses 1 minus 0. So I get 7 times 1, which is 7. This time, the integral converges. Converges to 7. We went over case 1, case 2. Now, next example is when we have both negative infinity and positive infinity at the same time, case number 3. So take a look at this. We have a negative infinity to positive infinity. So we are going to be separating. Okay, separating in the middle part. Also here, we have a last problem ending with application problem. And this is very similar to number 10 on your homework problem. So we have 2 more examples to go. So here, we can break down, we can pick C, and C can be any point. Okay, so I'm just going to pick 0 right in the middle. Negative infinity to 0, 0 to infinity. So you have negative infinity to 0 of 4x. So C in my case is 0. You don't have to use 0. C can be any point. So you can pick 1 if you like. You can pick 2 if you like. You can pick negative 5 if you like. I just like 0 because it's simple. So that's why I decided to use 0. And then we have 1 plus 2x squared whole thing squared dx. 0 to infinity, 4x. We have 1 plus 2x squared dx. Okay. Continuing. So this is like case A and this is case B. Case number 1 and second one is case number 2. Because we have negative infinity to, this is like case number 2. Let me rewrite it. This is number 2 and this is number 1. Because number 2 has a negative infinity to the number and case 1 has a to infinity. So I'm going to use this definition to rewrite both. So this changes to limit as a goes to negative infinity, a to 0. So this part is the modification of 4x over 1 plus 2x squared dx plus we have same thing, limit as b goes to infinity, 0 to b. So this part is the modification. So this infinity, we put limit as b goes to infinity. 4x over 1 plus 2x squared whole thing squared dx. So next step, let's do one at a time. Let's start with the first one. This requires a u substitution. It's not a simple integral, so this requires a u substitution. In fact, both, right? They're same integral, so I'll apply the u substitution. And my u will be 1 plus 2x squared. So my du will be 4x dx, which is nice. You see that 4x dx. So applying the u substitution, I'm going to have limit as a approaches to negative infinity. And then this will be still a to 0. This part is u. So u squared, and this part is du. So I have 1 over u squared du. And then same thing, limit as b goes to infinity. I'm going to have 1 over u squared du. Now I'm going to move this problem. the next page so we have a space. And I will erase this. Okay, so let's keep going. Now I'm looking at this and I need to take the antiderivative of u squared, which is u to the negative 2. You can think of 1 over u squared as u to the negative 2. So we raise power divided by new power. Negative 2 add 1 is negative 1 divided by negative 1. My integral will be negative 1 over u, evaluating from a, this is a, to 0. Similarly, limit as b approaches to infinity, negative 1 over u, 0 to b. Let's plug it in. Limit as a approaches to negative infinity. You have negative, so substitute u back, 1 over 1 plus 2x squared, a to 0. Limit as b approaches to infinity. Again, back substituting u back as 1 plus 2x squared from 0 to b. Now plug it in 0a and then b and 0. I'm going to get the first term, this part here, as, if I plug it in 0, I'm gonna get negative 1, 1 plus 2 0 square, and then minus 1 over 1 plus 2a square. Negative 1 over 1 plus 2b square minus 1 over 1 plus 2 0 square. Okay, limit, let's simplify. So I'm gonna get negative 1 over 0, so 1, negative 1 over 1, plus, because negative times negative is a positive, 1 over 1 plus 2a squared. Limit as b approaches to infinity. I'm going to get negative 1 over 1 plus 2b squared plus 1 over 1 plus 2. 1 over 1 plus 0, because this part is a 0. So this will be just 1 over 1. All right, so plug it in, negative infinity to this. Let's see what happens. Then this part is still negative 1. Now you have negative infinity, square that. That's a positive infinity, double that. And then I'm just going to have 1 over infinity. 1 over really big number is 0. Similarly here, if I plug it in infinity, I have an infinity square plus 1, that's just infinity. So negative 1 over infinity really is a 0 again, plus 1. So I'm going to end up having negative 1 plus 1. So they cancel out. The whole thing ends up being 0. So the integral converges. Okay. So this seems a lot longer because you have to separate it into two integral. but the whole process is still the same. Rewrite it into limits and then take the integral and then evaluate. Let's move on to a last problem, which is an application problem. Okay. So let's take a look at number 5. It is estimated that an oil well will produce oil at a rate of R sub T million barrels per year, T years from now, as given by R sub T equal to 10 times E raised to negative 0.04 T minus 10 E to the negative 0.2 T. Estimate the total amount of oil that will produce by this well. All right, so we have an oil rate given from now all the way up to infinity. So that's the key point. So we have this starting point all the way up to infinity. And our goal is to find the total amount. So this word, the total amount, is a key clue that we need to take antiderivative. So note, at some point in the future, the annual production rate will become so low that it will no longer be economically feasible to operate the well. However, since we don't know this, when this will occur, because you know that we will not always have a oil, it's a depleting resource. So at some point, we know it's not gonna have a large amount of production, right? But we don't know that. So we'll assume that well is operated indefinitely. So we'll use the improper integral. Okay, so we are not gonna pick a number because we don't know. We'll just stay indefinitely. So we'll use an improper integral. So I want to make a statement and write it out what I just said. Note, at some point in the future, the annual production rate will become so low that it will no longer be economically feasible to operate the well. However, since we do not know when this will happen, so we will assume that the well is operated indefinitely. So we use an improper integral. Okay. So this is what we are doing. 0, counting that this is year now, all the way up to a certain point in the future, but in our case, we will assume that it works indefinitely, of our rate function. Okay. So this is case 1. We have a 0, a number to infinity. So we will rewrite it using limit as b approaches to infinity, 0 to b. And our r sub t is 10e raised to negative 0.04 t minus 10e raised to the negative 0.2 t dt. Okay, so this is 2 terms, so you can take integral term by term, but looks like we need a u substitution, right? So let's do the u substitution on the first one. So this one I can apply I can make this one as a negative 0.04t e to the u. So my du will be negative 0.04t. And then this part here, my u will be negative 0.2t. So my du will be negative 0.2 dt. Should be dt. Ah, yes. So t is our variable. Okay, so let's continue. So limit as b approaches to infinity. This part here, so now it's going to be 0 to b 10 e to the u dt. But you can see that, let me word this. So if I continue and solve for dt, I need to have du over negative 0.04. So that's what the substitution will do. So my limit as b approaches to infinity, 0 to b, 10 times e to the u, and then you have 1 over negative 0.04 du. Simplifying, 10 divided by negative 0.4, 10 divided by negative 0.04, I'm gonna get negative 250. So I'm having 0 to b, negative 250 e to the u du for the first function. Okay. Similarly over here, this part I haven't finished. So subtracting ten to the 0 to b, 10 to the e to the negative 0.2 t, so this will be e to the u dt. dt in this case will be dividing by negative 0.2, so I'm going to have du over negative 0.2. So plug it in, I'm going to have limit as b approaches to infinity, 0 to b. This part is e to the u dt is negative 1 over 0.2 du. Dividing this negative with the 10, I'm going to get limit b approaches to infinity, 0 to b. That will be 50 e to the u du. Plug in back. Now e to the u, that's easy one to integrate. That's just e to the u. So my limit as b goes to infinity, after you take the antiderivative of this, I'm going to get negative 250 e to the u, but plug it in u back, I'm going to get 0.04 t from 0 to b, and then subtracting limit as b goes to infinity of 50 e to the negative 0.2 t from 0 to b. Now, because they're exactly the same limit and then same number, I'm just gonna combine back into one integral, so it's easy for me to plug it in numbers. Actually, I wanna make this one smaller size, so there's a space. Let's put it into one function, negative 250 e to the negative 0.04t plus 50 e to the negative 0.2t from 0 to b. So if I plug it in, I'm going to have, if I plug it in b into this, I'm going to have negative 250 e to the negative 0.04b plus 50 e to the negative 0.2b. Now, if you plug it in 0, anything to the 0 power is 1, so I'm going to get negative 250 e to the 0 power plus 50 e to the 0 power. So this part over here is negative 250 plus 50, which is negative 200. With this negative will make positive 200. Right? This will be negative 250. This will be plus 50. So that will be negative 200. With this negative will make positive 200. Oops, don't forget, I should have really put the limit in front. I dropped the limit. That's my mistake. The limit, we still have to apply limit because we haven't done so. Okay, so now plug it in infinity to here and here. I'm going to get, this part will be like negative 250 over e to the infinity because it's a negative power. 50 also e to the infinity. So this will really be 0, 0. So leaving us with about 200. The last surviving term is a 200. So what does this mean? The total production of any finite time period from 0 to a b, right, certain number, is less than 200 million barrels. Okay, so this is what the interpretation means. The total production over time period 0 to b, certain number, is less than 200 million barrels. Okay. All right, that's it for section 11.1, and on next video we'll move on to a next topic.